Hello, welcome back to Cracking the Cryptic. So much going on around the channel as always. We've got our Killer Sudoku app is one of many apps. If you enjoy today's Killer Sudoku puzzle, you may want to check that out because there's a lot of, well, I'm not going to say similar because I don't really know what we've got in store today, but there's a lot of Killer Sudoku puzzles in it, unsurprisingly. And like our other apps, it is very good value, as is, of course, joining our Patreon, where there's always loads of extra content, including Blobs' masterful Lord of the Rings hunt. There's our merchandise and Sven's Sudoku pad, all on the links under the video. But the first link is to this puzzle. Now, Jeremy Butler, aka Quarter Through, was a very regular contributor to the channel, and I use the past tense, was there, because I think we were at one point doing a puzzle of his every week, roughly. But we haven't heard from him for 2 years. And here he is, suddenly back in our inbox, back with a killer Sudoku. No frills. Even the blue in the grid is just decoration. You can ignore it in terms of solving the puzzle. And it promises, therefore, to be very interesting that Jeremy has re-emerged. I don't know what he's been up to for 2 years, but I hope he's been having a great time, and I hope he's come back with an absolute banger, and we'll see. Do give this a try on the first link under the video. I'm going to do the rules, which won't take very long. The normal Sudoku rules apply. 1 to 9 goes in every row, every column, and every 3x3 box. Oops, that's not quite a 3x3 box, that is. In every cage, the sum of its digits is given. And that's it. We don't even need the normal rule about digits cannot repeat in a cage, because every one of these cages is confined to a 3x3 box, so they couldn't. Okay, give it a try on the first link under the video. I think we'll probably all discover something interesting, but let's get cracking now. Okay, well, this gives me a chance to share with you a bit of a secret. Some people know this already, but not everybody. Every row, column, and box in a Sudoku adds up to the same number. It's incredible, but it's true. And we know the number. It's 45, because that's the sum of 1 to 9. And what that means is that in this box, we've got 6 cells there adding up to 24, according to their cage totals. We subtract 24 from 45, and these, which I shall call yellow, because they now are, add up to 21. Now, there are 3 ways of making up 21 with 3 different digits. They are 984, 975, and 876. I'm just going to aid memoir write those combos down because it's quite interesting. There is an aspect of them that is quite interesting and quite relevant. Let me just colour that 21 cage green. Obviously that is made up of one of those sets of 3 digits as well. Now, first of all, I'm going to prove that green and yellow are not made up of the same sets of 3 digits, the same one of these sets. If you were to put 876 in green and 876 in yellow, where would 876 go in row 3? They would all be packed into this cage, because they wouldn't be allowed in boxes 2 and 3 anymore. And then they would have to add up to 21, and this cage doesn't. It adds up to 11. So green and yellow are not the same from these, I wanted to call them pairings. They're not pairings, they're sort of treblings, trios. They're not the same pair of trios, the green and yellow areas. So one of them is one of these, and one of them is another one. And the interesting thing about that is there are 3 ways of connecting 2 of these trios. That is one, that is another, and that is the third. But each of those ways shares a digit. Now I'm getting excited about that, and that is because once that digit has been kept out of these cells, in row 3, where it must appear once, it's got to be in the 11 cage. And the shared digit is either a 9 in the case of those 2, an 8 in the case of those 2, or a 7 in the case of those 2. So this cage has one of those digits in. Now it cannot have a 9 in, because it's an 11 cage and the 2 other digits would both be a 1. So it's either got a 7 or an 8 in. And the other 2 digits in the cage are either 1, 2 or 1, 3. And now we know there is a 1 in the cage. And that means this 7 cage is either 2, 5 or 3, 4. And it means that these green and yellow are not that pair, so one of them is 6, 7, 8. I don't know which one though. And I don't know which the other one is, so maybe that is a bit limited. I can see that we're going to get a very similar situation down here, actually. I'm just leaving those aide-memoirs there for the time being, but I am remembering that they're there. Okay, the similar situation we're going to get down here, there's a lot of symmetry about this puzzle, not just in the positioning of the cages, but the numbers. And I think you will find that a lot of these cages add up with their symmetrical counterparts to give it the size of the cage multiplied by 10, which is quite interesting and very deliberate, very deliberate. Leaves me wondering where exactly the symmetry will be broken in the puzzle, but that's not a problem for now, or indeed necessarily for us at all. More a problem for the constructor. But okay, what I'm learning down here is those 6 cells add up to 36. So these 3 add up to 9. Now, just as 21 has 3 ways of being put together, so 9 has 3 ways of being put together. And there they are. And just as up here, each of these trios, or well, each pair of these trios shares a digit. Those 2 share 1, those 2 share 2, those 2 share 3. And since let's give this a colour, we'll call that red and this purple. Since red and purple do share one of those low digits, 1, 2 or 3, this cage has one of those low digits. Well, it can't have a 1 in, or the other 2 digits would be 9. It's very analogous to what happened up here, but with low versus high. Anyway, no, that's wrong. There's no 1 in it. There's either a 2 or a 3 in it. And now there must be a 9 in this cage, and either 8 or 7 to make up the totals. And now there's no 9 in this 13 cage. The analogies just go on with that cage now. That's either 8, 5 or 6, 7. And these red and purple, sorry, do not involve those 2 trios. So one of them is a 2, 3, 4, but I don't know which one. And that is the end of the reasoning from the Polish jury. Now, I don't quite know what to do next. I need to... Seven and 8 will both have been used here, and 9. Oh, yes, that's huge. Right. This might be a lot of pencil marking to do. All of these cells are chosen from 1, 2, 3, 4, 5, 6. Now, how on earth do I know that? Well, it's what I just said, actually. This cage uses either 7 or 8. And this cage, which is either 982 or 973, uses the other of 7 or 8. So both 7 and 8 have been used up in the row now, in those 5 highlighted cells. 9 has also been used up in the 19 cage. So the remaining cells in the row, actually even including this one, are selected from 1, 2, 3, 4, 5, 6, which is a big slew of digits. And I wouldn't normally write them all into a cage as pencil marks, but it matters here because these are also from 1, 2, 3, 4, 5, 6, and that is a sextuple of such digits. And we're left with 7, 8, 9 to go in the box there. And I warrant that we can do the same thing up here. I suppose we could do it more simply by saying, where do 1, 2, and 3 go in this box? They don't go here, because again, 1 is used here, and either 2 or 3. The other of 2 or 3 is used there. So they don't go here, and they don't go in the 21 cage, because none of them feature in those trios. So they're a set there. And now what? Well, we can do... well, I could pencil mark these as from 4, 5, 6, 7, 8, 9, I suppose. Let's actually consider what green could be and what it would leave here. So it could be 4, 8, 9. Is that going to be the green digit that doesn't come from 9, 8, 7? I'm not sure. Right, if green is 4, 8, 9, and that's 1, 2, 3, this is 5, 7, 6. That's 3, 4, that's 1, 2, 8, and this is a 9. If green is 5, 7, 9, this is 4, 8, 6, that's 2, 5, that's 1, 3, 7, and this is 9 again. And if green is 4, 8, 9, 1, 2, 3, 5, 7, 6, that's 3, 4. Have I just tried the same thing twice? I just tried 5, 7, 9 and 9, 8, 4. Have I tried 6, 7, 8? Then this would be 4, 5, 9. Oh, that's impossible. I don't think I did try green equals 6, 7, 8. And I think it's impossible. Because if that's 4, 5, 9, you can't fill in this cage. So green is not 6, 7, 8. It has a 9 in it. There's no 9 there. And the 9 in the row is definitely here now. Now, this is exactly analogous down here. I must be able to do the same. I am about to get rid of these aide memoirs because they're going to start looking like actual pencil marking if I do much more. But just for now, I'm going to rule out this being 2, 3, 4. Which is the opposite case to that being 8, 7, 6. If this was 2, 3, 4, that would be 1, 5, 6, and you couldn't make up the 13 cage. You need either 5 or 6 in it. So this is not 2, 3, or 4, 2, 3, 4 specifically. It's got a 1 in it. There's no 1 in those cells, and the 1 in row 7 is there. And we have 2 digits in the puzzle, and we celebrate wildly with cheers and bunting. Well, we probably don't, but okay, I'm going to get rid of these aide memoirs now, because I think they might get in the way a bit. And you've probably understood the lesson, and I can remember the combos. Now, this, yes, we don't have a 1 in the red group because we have a 1 in the purple group. If we had a 1, well, we can't have, sorry, it's obvious, there's a 1 in the box. So that is a 2, 3, 4 set adding up to 9. You remember they had to add up to 9. This is an 8, 7, 6 set in yellow. Right, and we've got a 1 in that 17 cage, along with the pair that makes 7 that won't end up in this cage. And we've got a 9 in this 23 cage, along with the pair that make 13 that don't end up in that one. It's all very logical. But it does worry me that I'm going to be groping for any further conclusions. Well, there's a 1 there and a 1 there. That's a sort of virtual X-wing. That's going to use up the ones in column 4 and 5. So there'll be a 1 in one of these cells in the central box. Same with 9s there and there. It's got to be a 9 there. If I want to move on to the 6 and the 14 cage. Oh, maybe the 20. Okay, the 20 is interesting because if it didn't have a 9 in it, then the 9 in the box would have to be here, and the cage would be an 8, 7, 5 cage, and that would form a quadruple down here of 8, 7, 6, 5 with a 9 there, and everything else in the row would be from 1, 2, 3, 4. That's very prescriptive. So keeping 9 out of that cage is difficult, but it is just manageable, which is a pity. It's about the high digits in this column, and presumably the low ones in this one. It is, and I've finally figured this out, I think. I don't know, maybe I haven't. Just bear with me. Yes, okay. If I'd pencil mark these cells as, they definitely contain a 9 and either 5, 8 or 6, 7, but they're selected from those because 1, 2, 3, 4 have gone in this box. Now, this pair, look at this. This is either a 5, 9 or a 6, 8 pair, and that is a quintuple. 5, 6, 7, 8, 9. This has to be low. It's not the 7 or 8. Everything else in the column is from 1, 2, 3, 4. I feel that has to be interesting, but I don't quite know how. For the time being, I'm going to nip... Oh, no, hang on. The 7 in this column is in one of those 3 cells, so neither of these can be a 7 in the box. And that now can't be a 6 in this 13 sum. Okay, now I'm going to do this. This is 1 and 5 or 2 and 4. And these are also from 1, 2, 3, 4, 5. So this is our 1, 2, 3, 4, 5 set. The 3 is up there, so those can't have a 3 in, and this now can't be a 4. In the column, these other digits are from 6, 7, 8, 9, including this one, which can't be 2 or 3. Now, where does that leave us? Still, this can be 8, 7, 5, and that can be 9. Can that be 9? Yes, that can be low. In fact, it's almost begging to be at this point. That 1 and 9 didn't really do anything. I mean, I am beginning to assume that this... I don't know. I was going to say, I'm going to assume that this puzzle now always has symmetrically opposite cells adding up to 10. But given the markings in the puzzle, the placement of the cages and the fact that symmetrically opposite cages add up to 10 times the number of cells, I'm not sure you could disambiguate the puzzle if that was entirely true. And there'd be 2 solutions. I'm not going to use uniqueness. It's just a factor that I'm commenting on at the moment. Now, this is not a quintuple, sadly. One of those is a 3. Oh, hang on. Okay. This is not a quintuple, but it is a quadruple plus either 2 or 3. Oh, that's really weird. Why can't I see that? Yeah, this cage contains 2 big digits, either 7, 9 or 8, 9. In fact, it contains a 9, so there's no 9 there, there's no 1 here. Now, the thing I was just getting to, and this is really important, is 4 of these cells are 6, 7, 8 or 9. They have to be. I am right there. I am right, yes. So this T contains all the big digits once, and I mean 6 to 9. 2 of them there and 2 of them there. Yes, okay. So these are from 1, 2, 3, 4, 5. Now, this bottom row, we've got a 1, 2, 3, 4, 5, 6 quad, which stops that being 6 and that being 5 or 6. But so they're a 7, 8, 9 triple. I think what is far more important for us is what it does with 6 in this row. It puts it in this box. And this must therefore be a 6 to 1 cage adding up to 9. With the 6 in the bottom row. And these aren't 1, 2 or 6. They're a 3, 4, 5 triple. And we're in business. We're totally in business now. We take 3 out of that cage, and now 2 is in it, so 2 can come out of those cells. This pair, hang on, 2 is in it. We can get one of the big digits out as well. 2, 9, 8 is the right total. So that is a 2, 9, 8 cage. So in fact I can now fill in these digits, 7 there and 6 there, and these are 7 and 6 as well. We're at 6s and 7s in a way, but not in the meaning of that phrase. Hurrah. Now, there's no 7 there. There's no 6 here. There's a 5, 7, 8, 9 quad, which needs a 5 in one of those cells and not in one of these two. A 7 in one of those cells and not here. And there's a 1, 2, 3, 4 quad. Oh no, I was going to say, where's 5 in this row? But I've already confined that to box 9. Now, 6 and 7, how are we using them? Right, this can't be a 5-9 cage anymore because they would both have to be 8. Oh, the pencil marking is the key to success here. That's a 6-8 pair now. This is 9, that's 5, 8 there. Now, I must be able to replicate all this up and down here somehow, if I can just remember how. That's not 6 or 7. I've got an 8-9 pair. That's not actually what I just did over the other side, but never mind. It's still true. Is it... How did we get going? I worked out what was in the equivalent of this cage. Yes, there's a 1, 2, 3, 4 quad. In those cells, 2 of them there and 2 of them there. That's the equivalent thing. There's a 1, 2, 3, 4 quad there. These cells are from 5, 6, 7, 8, 9. Is this going to work up here? I'm not actually sure it is, but it probably is because everything else has been so symmetrical. This cage, I mean, I could literally pencil mark it as 4, 5, 6, 7, 8, 9. And here is my sextuple in the top row. 4, 5, 6, 7, 8, 9 there. So the other cells are from 1, 2, 3. Now, the important thing about this is that 4 is confined into green. So one of those is a 4. And that's not a 4. But this is a 4, 8, 9 cage. So this is a 5, 6, 7 set. So this doesn't have a 5 in and is a 3, 4 pair that we've placed. And now there's no 3 over this side, and therefore no 7. And therefore this is a 1, 2, 8 cage. And therefore we fill in 3 here, near the corner. 4 there. This is 1 or 2. And there's my symmetry of a 1, 2 pair there with an 8, 9 pair here. Now there's no 3 or 4 in this cage. It's a 1, 2, 5 set. And that fixes this. This can't be a 1, 5 pair, or they'd both be 2s. So it's a 2, 4 pair. That's a 1 above a 5 with a 2 on their side. And that fixes this cell, 8, 9, 2. That's now not an 8. Something does the same. Yes, 8 is looking up at that cell. There we go. 2, 1, 8. No 8 in those. That's become a 2. And that's become an 8. Now, this is either 9, 3 or 7, 5. Let's tidy up the Sudoku. No 4s on that side. If that was 9, 3, this is 1, 5. No, that works. If this is 7, 5, that's 6, 8, and that's 1, 3. So both of those work. Bother. Oh, there's an 8, 9 pair. That's huge in this column. Didn't see that coming. That makes this a 7, and it makes this a 4. Let's get rid of those last corner marks. That's now not a 7. I can see a 1, 2, 3 triple, which I'm going to use. It's not quite the equivalent of what I saw on the other side. I probably missed some pencil marking, but that can't be a 6 now. There must be a 3 in one of those cells. Oh, yeah, oh, look, in the top row, that is a 2. And now this is a 1, 3 pair, but that's become a 1, that's a 2, that's a 1, that's a 3. Loads of digits. We've got 8, 9 pairs in both columns 5 and 6. That's not a 3. Oh, they're resolved by this cell. I was thinking they can't be resolved on one half of the grid, at one end of the grid and not on the other. No 9 there, no 8 there. We've placed 8 in box 1. This is a 2 in box 7. 3, 4 pair looking across at a 1, 5 pair in the bottom row. And therefore that's a 3 and that's a 4 in box 9. Now, these can't be 5s, so 7 and 6, and a 5-9 pair above. Is that right? Yeah, I think it is. Yeah, and we've got these matching pairs going on now, which feels righteous. Now, this cage, the 10, well, since I couldn't work out the 20 cage, I probably can't work out the 10 cage. It either has, oh no, I can. So something's moved on. This can't have a 1-7 in it to make up the remaining 8, or 2-6. So it does have 3-5, and that's going to sort out. Oh, well, look at what I've done here. I've left the wrong pencil markings in. Should have been a 3-4 pair, but it doesn't matter because they're fixed now. 4-3. That's become a 9 thanks to the 3-5 pair. This is a 1. This is a 4-7-9 triple. Now I must have been able to do the same over here. Now this can't be a 3-9 pair since we got that. That's why. 5-7 there. 1-5. 7-6. I've got a 9 to put in there. And a 1-3-6 triple here. That can't be a 1, and that can't be a 1 anymore, and that can't be an 8. That's bigger news. This now can't be a 6, and it is fixed as a 3. That can't be a 9. I must be able to do something equivalent, but I'm placing 8 in the central box first. That's the only place it can go. Yeah, that 2 is looking at this cage. 4 and 2 there. This is a 7, and those aren't. And we're reducing everything in rows 4, 5, 6 to pairs, which is great. 2s. Got 4 2s looking at the central box. If you ever have 4 2s looking in the box, even in classic Sudoku, you can fill in that digit in that box. Now, this is probably, this is going to be where the symmetry I was talking about of digits being rotationally opposite symmetrical digits which complete their sum to 10. So those two add up to 10, those two add up to 10. I rather suspect anywhere you go in this grid at the moment, that is applying. But I can tell you that it's not going to apply to these cells because of the total here. The total of this cage is 24, we're given that. Plus 10 there is 34. These two add up to 11 and not 10. Oh, and therefore they don't include 9 and 1. Because a 9 would, in one place would need a 2 in the other. And a 1 in one place would need a 10 in the other. And that can't happen in this thing. So we do get to put the 9 and the 1 symmetrically opposite each other there. 6 there. 4, 9. This is a 1. Now, these add up to 11. They are not 9, 2 or 8, 3 according to the box. They're also not 4, 7 according to that row. So they are 6, 5, breaking that symmetry. Weird to me that that gets broken this late and only just. I might actually spend a moment or two at the end analysing how many cells are not symmetrically opposite their 10 counterpart. Because I think it's only going to be about 2 pairs. And I mean, this puzzle is finishing. Let's just get rid of the colours because we can't get rid of the blues that were provided, but I can get rid of all the colours we used. 4, 7, 3 finishes this off. The cage will add up to the right total. Yes. There we go. What a brilliant puzzle. That is just magnificent by quarter through. No wonder A's appeared again to send that to us. Send us more, Jeremy. Send us more because that is great. And Killer Sudoku Storm. It was a perfect storm. Now, 9, 3, 5. I'm just going to highlight the cells at the top of the grid that obey being opposite the 10 counterpart. Ah, look, these don't. In this box. This is weird. This is like a discovery of something that's just wrong in the universe. 2, 5, 8, they do. 9, 3, 4. You see, everything else in rows 1, 2, 3 do. 1, 6, 9 is opposite 1, 4, 9. 3, 8, 4. That one doesn't. And that's weird because it's in a cage. So, sorry, where did I have it? I had it as those two and those two not matching their counterparts in adding up to 10. Then I've just discovered this one and this one, this one and this one. I think that's all. And then in the central box, obviously, we had 5 and 6. So there, those are the digits in this puzzle that are not symmetrically opposite a number that adds with them to 10. And there are very few of them, and it's intriguing to me that there is a formation of the grid that does that. And look how it doesn't disturb the cage totals from if it didn't act that way. If that was 5 and 7, and that was 6 and that 5, that would be 6, that would be 5, that would be... I don't know, it doesn't work. I don't really understand what's going on, but it's fascinating. Jeremy Butler has completely sold me a dummy there. Anyway, brilliant puzzle. I'm really glad to have done it. Hope you had fun with that one. And do join us for more again tomorrow. Bye for now.